So can you remember the last time you went to like an art gallery or a live performance and you couldn't really enjoy it because everybody was taking photos with their phones? So this is a reality. It's not just kind of image sharing. People are on social media all the time. They do video on demand on their mobile phones and so on, which means that at the beginning of the year, we've been seeing over 100 exabytes of mobile traffic per month globally. Let's pause here. You know what that means? 100 exabytes. That's 10 to the power of 20 bytes of traffic every single month, generated by humans with their phones or consumed. Okay, so if that wasn't enough, now we have devices that generate data or consume data. For instance, in industrial automation settings, where you have robots that get all sorts of commands or transmit telemetry to some command center. Or in the case of autonomous transportation, you have shuttles that are unmanned. They have a host of sensors that they are equipped with, and they sense all sorts of things, visually, speed, and so on. And then again, that information is being relayed over a mobile network to some command and control center. Okay, so what? Well, there's a lot of pressure that is being put on the network, and the networks as a result have become very complex and extremely difficult to manage. And frankly, the end users are not really satisfied with the performance that they get from the network itself. So we have 5G being deployed now. The sad news is that this has really poor return of investment. So at the moment, 65% of the revenues that come from running those networks goes into operating costs, and that includes energy costs, engineering time, and so on. The networks themselves are being managed by experts over dashboards with, for instance, alarm systems that get triggered every time a threshold is being crossed. So there's no real automation. So you have these static thresholds that are not really specific to any part of the network. It's kind of one-size-fits-all type of deployment, or you need a lot of manual configuration to be able to configure those thresholds at every different location, and again, more manual work, tedious work, and so on, which means cost. So obviously, operators want to understand a little bit better whether they can anticipate the demand so that they can allocate resources ahead of time to meet their customer needs. So there has been some level of kind of forecasting that is being implemented. Unfortunately, the current tools are quite poor in terms of accuracy, and forecast is being basically deployed at the level of individual network element, let's say at the level of a base station or an antenna. So that translates into poor scalability. You have to train a neural network, for instance, for every single location, which really doesn't scale. Okay, so what's changing actually? Things have to change, right? Everybody's consuming traffic and so on. So in the end, somebody has to pay for it. Somebody has to make some money, because otherwise we wouldn't have all this infrastructure that we rely on every single day. So there's a new concept called network virtualization, by which mobile network operators are moving from using dedicated black boxes that implement different functions, which basically belong to certain vendors, and they have very little control over them. So these are your Nokias and Ericssons and so on, and you have functions that do, for instance, mobility management or signaling or whatnot. And these are expensive tools, and they have very limited sort of flexibility on what you do with them. So the change is in terms of taking the functionality that these things provide, implementing that into software, and then deploying that software into virtual machines or containers that now you can run on general purpose compute. So that's kind of nice. You can deploy that on-prem or in the cloud and so on, and it gives you a little bit more flexibility, but at the same time, kind of unlocks this sort of vendor dependence. At the same time, you're having kind of the ability to understand, where you need resources, and you are looking at underpinning this new type of lucrative services, such as, for instance, autonomous transportation. The question is it? Are we really there just yet? Well, not really, because if you want to kind of, understand where you need compute power, where you need capacity, you need to have real-time and predictive knowledge of the demand that these applications pose on your infrastructure. And that's going to be essential both for the management, the effective management of that infrastructure, and for monetizing it. So this is some of the stuff we are doing with my team at NetAI. So one of the problems we tried to tackle was understanding how much traffic, let's say your YouTube, your Netflix, your Spotify, and so on, consumes at any given point in the network. And how can we do that in a non-intrusive way without looking on the data path, without needing to understand what a user is doing on the network, without caring about encryption, without waiting days for that information to kind of be available to us so we can take decisions in real time. So what we do here is, this is an example, so you can measure information at the level of an antenna, so that's what you see at the bottom, so that's the traffic aggregate. And we want to disentangle that into the services that make up that aggregate. And then we want to be able, so that's the concept that we kind of call decomposition. And then we want to do that at different sort of geographical levels. Maybe you have clusters of antennas that are managed by, let's say, a set of virtual machines, and I want to understand demand there. But also maybe I want to do this at the level of a city-scale deployment, which is something actually we can do now within a second, which you wouldn't be able to do with traditional tools. So how do we do that? Well, we basically try to exploit spatial and temporal correlations that are characteristic to mobile traffic. And I'll speak a little bit more about that, and then if you want to have kind of a more deep dive into this, we can chat afterwards. So just kind of a high-level view. So normally, you have a deployment where you have a cloud of antennas, yeah? So you collect telemetry from these antennas, and you want to figure out what's happening there. So the first thing you do, let's say you want to deploy a neural network. Let's say you want to do convolution over that signal that is being collected at different points. So for that, your input has to be in a kind of a matrix form. So you have to do some mapping. So the first step is kind of pre-processing. So here we're converting that into a grid by trying to minimize geographic displacement. Why? Because as I said, there are spatial correlations that are key to disentangling those traffic streams. So that's the first step, and we've done that, and then you have snapshots of traffic demand on aggregate across your deployment, let's say for a very recent historical period, which look at like these 3D plots, yeah? So imagine it's almost like having images, and you don't have the intensity of pixels, now you have the intensity of traffic. And then you feed those aggregates into a neural network that learns to basically map those aggregates into time series of services that comprise those aggregates. Okay? And then you can do that with multiple structures depending on the sort of complexity and temporal granularity you want to obtain. In our case, we have sort of a proprietary neural network that does this in a really smart way. Probably we cannot talk so much about it, but the idea is that basically you can try different models. This doesn't have to stick to a certain type of neural architecture. And then there's some technicalities to do in terms of how do you train the model, what kind of loss function you choose, and so on, and then you need to normalize the output as well. So finally, you will have snapshots of these services that are of interest, so things like, as I said, YouTube, Spotify, Google Cloud, and so on. And then if you want your infrastructure to kind of cater to those services in a particular way, because now you deployed virtualization, you're trying to share a physical infrastructure among multiple applications on virtual networks, you can do just that. So let's look at an example here. So this is information that our microscope tool will ingest. So that's traffic normalized over a couple of days, aggregate information, and let's say we want to understand 3 different services here, Spotify, Facebook, and Snapchat. So what you see with red in all the other plots except for the input, that's ground truth. So that's kind of something we measure against to see how well we do. And then with blue, that's the predictions that we make. So you can see, I mean, the output of the neural network matches quite closely what's happening in the network once you have that information sort of retrospectively. So that's pretty good, because now you can use all that information to drive your resources. Okay, so then you'll say, hey, this is great. You have this information in real time, but it takes time to power up these resources. So can I do this ahead of time? Can I know what the demand will be for these applications or for a service in the next half an hour, in the next 1 hour, so I can, have enough time to make sure that everything is wired up properly and so on. So for that, we have another tool which we call NetSibula. You probably know why. If not, I can explain later. But the idea here is that what we try to do, instead of doing all that pre-processing initially, said, well, why don't we take those antennas and just try to build some graph-based representations of a deployment and do forecasting straight on the deployment. So what we do, we build coverage areas for them, these so-called Voronoi diagrams, and then we have a connected graph, and then we start pruning some of these edges between locations that are very far apart, just to kind of simplify the input. And then an important part here is how do you train such a network from like a super practical perspective. So here we came up with a sort of a dedicated loss function, which we call an operator monetary cost function. So this has kind of two components. One has to do with basically with the penalty. So the idea is here, if I have a deployment, and let's say I have an enterprise customer that pays for a certain service, every time I'm not able to provide enough capacity, for instance, and I violate that service level agreement, I pay a penalty, which is fixed, okay? And I want my neural network to learn that and never under-provision. At the same time, if I over-provision, the more resources I throw at the deployment, the more I pay. So for instance, if you're using AWS and you keep a VM running all the time, you're going to have a hefty bill at the end of the month if you didn't really use that, right? So it's kind of the same principle applies here. So you want you want your neural network to learn not to over-provision, just to throw enough resources to meet that demand in a cost-effective way. So what does that really mean? So if I want to forecast now, and I have service traffic, which you see there with like a light color, when I do forecasting, I kind of ride that demand. I just slightly over-provision all the time, yeah? And that's on purpose. And why do I want to do that? So if you look at the plot on the bottom, that's your prediction error. The error is kind of small, but you see one important element there. That error is almost never negative, which means I almost never underestimate, which means I will almost never pay any penalties, yeah? And instead, okay, I make some mistakes. There's a lot of variability. You can't make perfect forecasts. We try to do some of that with a bunch of other tools where we don't predict a single time series. We predict some confidence bands, which give us some degree of certainty about where a specific signal will lie, rather than having a single time series. So this is nice, not only because it avoids this problem of like under-dimensioning or over-provisioning, but at the same time, we make forecasting at deployment scale, which means we don't need to train an individual model, which means orders of magnitude fewer parameters to learn that, say, state-of-the-art long short-term memories that you would deploy at every single network element. Okay, so let's see an application of that. So there's a new philosophy here called the Open Radio Access Networks, or Open RAN. So the idea here is you're trying to kind of disaggregate the infrastructure and have more flexibility and create a sort of a level playing field by which you have different providers that come and can offer software or hardware and so on, so you don't rely on a single vendor. You're no longer happy with the solution, you just replace that because you have open interfaces and so on. So what we did, we said, okay, so you have a deployment like the level of a city where I have different so-called centralized units or CUs which manage a bunch of antennas, and I want to understand how much compute resources I need to drive those CUs. So I'll collect aggregate traffic information and provide that to a so-called XSUP that runs with a controller, and that XSUP embeds our forecasting engine, which basically takes that traffic information and tries to understand what will happen, say, in the next half an hour. And then it translates that traffic information, that traffic forecast, into capacity values, meaning how much compute power I need to drive those resources. And then I provide back the capacity values to the clusters, and I run the network in a kind of an efficient way. So I'll show you a quick demo of what that means, and then I'll close. So this is an example where basically you see, I mean, it's sped up. The information in the network typically gets updated every 5 minutes at best. Currently, it's going to change. But the idea here is that you have a continuous line where you have like the actual traffic if you had perfect information, and then, oh, I can't stop it. So the dashed line were the forecast that we make, which you can see here again, that in theory should match very closely traffic information. And on the right-hand side, you have the capacity allocations. On top of those bars, you see some dotted lines. That's perfect capacity allocation if I was an Oracle. So you see we were quite close to that, meaning that we always provide information of how much compute power you need at any point in time. So these kind of tools that we are developing and some other things that I didn't talk about today pave the way to kind of better and more efficient management and monetization of virtualized mobile networks. Thank you for your time.
Thank you. Thank you, Paul. Appreciate it. We have time for a couple of questions before lunch.
Hi, thank you for your discussion, very interesting. So I was thinking about the neural networks you're using for the temporal spatial information.
Yep.
And I think there's some obvious things that you could think, like industrial centers will require more during the weekdays, and maybe Netflix will be spread out on Friday and Saturday. But I was kind of curious whether using these approaches, what kind of non-intuitive, perhaps very small spatiotemporal scales or on very large spatiotemporal scales have you been able to draw conclusions about like behaviors of people on these networks that maybe nobody would have thought about?
Yeah, it's a good question. So there's 2 points you touch on there. So it's sure you can collect data and say how much traffic do I have, let's say on a Wednesday afternoon for this type of service at 5 o'clock. So that's statistical information you can obtain, and traffic will vary around that. It's never super accurate. So here, with what we do, we basically forecast with very fine time granularity, and we do that in real time. So I know, let's say in the next 5 minutes, how much traffic you will have. And it's not just a statistical, it's like, let's say if I can reduce that prediction error by 40%, that means a lot of cost. Say I use that to drive down compute, and I do that to reduce energy consumption. Especially today when energy is super expensive, I'm going to save a lot of revenue by doing so. Back to my point, which is operating costs are above 65% of revenues. So networks are really not monetized, and you already see people kind of doing mergers because they really cannot sustain their infrastructure anymore. So the second point is about correlations. I didn't show there. So one solution we have uses this so-called deformable 3D convolutional network. So we don't just the input is like a cube. It's no longer like a square and you scan it with the filter. You have a cube where basically you have traffic volume information at any point in time, and you do that over, let's say, past half an hour. So when you scan it, you don't have a cube filter, you have a filter that is non-homogeneous. So you try to learn correlations across multiple points in space and time, which become abstract, and then you use those to kind of disentangle the services. So it's not ever very clear what we know. There are some correlations in terms of like commute patterns. Say people leave work and you move to residential areas. So you're on public transport and you're watching news, for instance. So that's one thing you can see.
All right, any other questions?
Hi, my name is Eric. I work for Bell, and it's very interesting. Thank you. Do you think your approach can be useful for like call service demand? to predict how much call we will receive to like in 1 day or 2 days or in 5 minutes in your case?
They can certainly do that, yeah. We should have a chat, yeah.
Yeah, good. Thank you.
I think there's another question over there.
Hello, my name is Carla. I'm a student at Columbia University. I would like to know if your product could be scaled in other type of networks, not only mobile networks. And also, how can you integrate this in your own application? Basically.
Yeah. Valid questions. So first, the answer to the first one is this is not dependent on any sort of underlying technology type. So it can work with 4G, 5G, broadband, 6G, which is kind of growing up now. Because at the end of the day, I mean, we're just looking at distributed data sources that might exhibit some correlations. So for us, it's just like time series data with some location information. It just happens that we work on mobile networks because I'm an engineer by training, and I realized that networking community doesn't really have machine learning expertise, so I started understanding how to use some tools for that specific domain. And the second question was about how to integrate. So everything we build is kind of built on microservices. The demo I showed, it is an XSub, so we use an SDK from a virtualization solution provider, and we integrate with that. But it really depends. I mean, if you have time later, we have a stand at the back, and I can show you a demo. We have a front end. So for that, we use the REST API that is used by the front end to ingest the analytics that the AI engines provide.
Okay, I guess that wraps it up. Thank you, Paul.
Thanks for the
Appreciate
time, yeah.
Thanks for the questions, everyone.